Energy quiz. What are the units of energy? Are you sure? Yes. I didn't even get to write the question down. Okay, who can tell me another form of joules? Good. Otherwise known as Newton meters. Anyone come up with another combination? Yep, very good. Kilogram meter squared over second squared. And how would you remember this one? Well, if you think of the form of kinetic energy, it's 1/2 mass times the speed squared. Just plug in the units there, and that would tell you this one. This one, Newton meters, is exactly the form of work. You know, we're calculating work in some cases as, in the case of a constant force, we're calculating the work as the force vector dotted with the displacement, so that has to be newtons times meters. That's what you get when you take that dot product. But joules. Okay, so now, so that's the units of energy. What are the units of kinetic energy? That's a stupid trick question. It's not even a trick. It's just stupid. It's a kind of energy, so it's joules, right? What are the units of work? Yeah. You're all like, I'm not even going to dignify that question with a response. Thank you, George, for being the stand-up guy. Right. Any form of energy has units of joules. Okay. Work is a change in energy, so it has units of joules. Here's another question. Is energy a vector or a scalar? Is it a number, or is it or does it have direction? It's a scalar. And that's an important fact about energy. So there's no such thing as kinetic energy isn't down or up or to the left or whatever. Kinetic energy is just a quantity. Okay. So now going through the same thing, same set of stupid questions. Is kinetic energy a scalar or a vector? Okay. Is work a scalar or a vector? Vector? No, scalar. Okay? So those are important. The units are important, obviously. But this is an important thing to keep in mind about energy. If you ever do an energy calculation and you end up with a vector, you did something wrong. You took a wrong turn somewhere. Okay? That's true of work, kinetic energy, thermal energy, any kind of energy. Okay, so last time we came up with the work energy principle. And that says that if you add up all the work due to all the forces, that's equal to the change in kinetic energy. So this is the work due to all forces. And this is the change in kinetic energy of the object. Okay, so if you add energy to the system through work, is work positive or negative? Okay, so if you add energy, work is positive. And so what does that mean to the kinetic energy? Does the kinetic energy increase or decrease? it increases. So if you have positive work, you have an object that speed increases. Okay? If you add up the work of all the forces on an object, and it comes out positive, then the kinetic energy of the object's increasing. Its speed is increasing. Okay. In general, here's the bad news. Work total is equal to the integral of one force dotted with dr, so the line integral over the path of the first force, plus the line integral of the second force dotted with dr, and so on for all the forces. The examples we've done are simple cases. So we've done ones where these are relatively easy to calculate. But generally speaking, this is hard to calculate. Okay? But there's a certain type of force where this is always easy to calculate. It's easy if the forces are called conservative forces. And so this idea of conservative forces is a super important idea. It's a simple idea and it's important, and that's the combination you like, right? When the stuff that's important to remember is simple, right? When the stuff that's not important is complicated, you don't care. You just forget it and don't worry about it. But, okay, this is an important one to remember, and it's simple, so I expect you to remember this definition. So, conservative forces. If the object's location is all the information you need to know the force on the object, then that force is conservative. So the question is, okay, so if someone tells you the location of the object, is that enough for you to know what the force is on the object? If the answer is yes, then that force is conservative. If the answer is no, then that force is not conservative. And I'll give some examples. The two most important conservative forces in this class are an object's weight. Okay, so think about that. If we have an object, we choose an object and we measure the mass and stuff. And I tell you this object is a meter off the ground. Is that enough information for you to tell me what the force is on this object? And in fact, that's more information than you need with weight, right? Before you even tell me the location, the force is just mg down, right? But the key is, if I tell you the location, can you tell me the force? Yes. So that's a conservative force. And the second type that doesn't come up, weight comes up in pretty much every problem. This one doesn't come up as often, but the force applied to an object by a spring is also a conservative force. So if we knew the, let's see here. Okay, so if we knew the spring constant of this spring and hooked it to the wall or whatever, hooked it to something. Hooked it to George. George might move, so I want to hook it to something more stable. Let's hook it to this. Okay. And then hook an object up to it. Okay. And now I tell you the location of this object. Is that enough information to know the force that the spring's going to apply? Well, yeah, because remember that the spring force depends on the amount of extension or compression of the spring. And if I give you the location of the object, that's enough to figure out what that compression or stretch is. So a spring force is conservative. Yes?
But do you also know like the spring constant and the mass of the object?
Yes. Yep.
So are you assuming that
yes. For it's a given object, yeah. Okay. So let me give a couple of examples of non-conservative forces so you can see the distinction, okay? So here are two examples of non-conservative forces. Okay, so the first one is a normal force. So let's say we have this object, and we know everything we need to know about the object. And I give you the information that this object is sitting on the table here. Is that enough information to know the normal force that the table applies to this? It's not, because here are some examples. If I let it sit there, the normal force is relatively small. If it's still in that location, but I push down on it, now the normal force is bigger. If I pull up on it a little bit, now the normal force is smaller. So without changing the location of this object, I've changed the force that's applied to it. So that can't be a conservative force. Okay, any questions about that? Another one is friction. Okay, so say that at this instant, the object is right here. I tell you the object is right here. Is that enough information to know the friction force? No, because for one thing, if the object's here but it's moving that way, we know the friction force is that direction, right? If it's going the other direction, we know the friction force is that direction, so it's not enough information. Okay, so there are a lot of, yes?
In which category would you pushing on the thing fall into, like a non-conservative force or conservative force?
That's non-conservative. So we're breaking up the world into these two types of forces. Conservative forces, which we like because we're going to see that they're simple to deal with, and non-conservative forces, which are a little trickier to deal with. Okay? If a force is conservative, there are two properties about it that we're going to take advantage of. The first one is that it can be represented as a force field. Okay, so in Marvel Comics, force fields are these really cool things, but these don't have to be very cool. I suppose you could imagine ones that are pretty interesting, but like, for example, gravity is a force field, you know. In fact, if somebody, you know, if you're ever like cornered by a bunch of like robbers or whatever happens in like Spider-Man or whatever, and you're like, you better be careful. I can produce force fields, you know, because you produce a gravitational force field. I mean, they might not be, you know, it's a pretty small force field. It's not a very big force, but anything with mass produces a gravitational force. It's a conservative force, so you produce a force field. Okay? I don't know. It might not convince them not to take your wallet, but maybe. Okay, so what is a force field? So a force field, think of it like this. What's a poppy field? I'm drawing a poppy field. Those are poppies, as far as the eye can see. Don't make heroin out of them. These are just poppies for looking. Okay, so what's the idea of a poppy field? No matter where you go, what location you choose, there's a poppy there. You know what I mean? And it's the same thing. That's what a force field is. It just says no matter where you go, what location you choose, there's a force there waiting for the object. Okay? That location, a single location has a force associated with it ready to act on the object. Okay? So here's a poppy field. Wherever you go, there's a poppy waiting. A force field is the same idea. Wherever you go, there's a force waiting. So you can think of it as like this object that's being acted on by gravity. You can think of like force vectors, a force vector living at every location in space. And that force vector is like called into action when this reaches that location. You know what I mean? There's gravitational force vectors sitting at every location. I choose this location, and so the force vector that's in space there is the one that acts on this. Okay, that's what a force field is. The same with a spring. With a spring force, there's a force vector waiting at all these locations. I choose this one, and so the force vector that's in space here is the one that acts on the object. That's the idea of a force. The second one, this is the one that we're going to use directly, is, and so these are the two properties of conservative forces. So if a force is conservative, every location is associated with a potential energy. And so wherever the object is, we're going to be able to calculate this value called potential energy. And then the work done, so here's the reason that, so the usefulness of the potential energy idea is that the work done by a conservative force is equal to the change in potential energy. The negative change in potential energy. And this change in potential energy is the potential energy at the final location minus the potential energy at the starting location. Okay, so what's the benefit of this? What makes conservative forces especially easy to work with? If you look at this definition of work done by a force, okay, if, say, we don't know that this is a conservative force and we have to use this definition, the work done by that force in general depends on the path that the object takes to wherever it is. Okay? You get a different amount of work in general if an object starts here and then goes to New Mexico and then takes the train back here. You get a different amount of work than if this object just goes, okay, so say it goes to New Mexico and back and ends up an inch away. Okay? You get a different amount of work than if the object just travels that inch. With conservative forces, that's not the case, and you can see that from how we do this calculation. With a conservative force, no matter what the path is that the object takes, the work done by the conservative force is just the potential energy representing the final location minus the potential energy representing the starting location. Okay, so let me flesh that out a little bit. Anybody have any questions yet? This is all a little, it's a lot of words and no calculations. We'll get to some calculations. All right, so notice. The work done by conservative forces forces is path independent. It only depends on the starting and ending locations. That's not true of forces in general. Okay, so let's see a couple examples. Okay, so I'll demonstrate this. By doing a work calculation for friction. following two paths. And then for a conservative force following two paths. Okay, so what's going to happen here? So for friction, I'm going to have an object start at a location and end at a location. Those starting and end points are going to be the same in both cases. But in between, the object's going to take different paths. Okay? What do you expect for the work done by friction for those two different paths? They're going to be unequal because friction is a non-conservative force. Okay? Then I'm going to do it for I'm going to make up a conservative force where the force depends on the location. And I'm going to do the same thing. We're going to start at a given location, end at a given location, but take different paths to get there. And in that case, what do you expect? They'll be the same. Thank you, Grady, for your courtesy. Screw you guys for your lack of courtesy. Okay. So friction. So case one, well, so let's say that the force of friction is 10 newtons. And remember that the force of friction always points opposite the velocity vector. And let's say the starting position is always going to be the origin, and it's always going to end at 3 meters. Position equals 3 meters. But it's going to take different paths to get there. So case one, the object's going to go from the origin to 5 meters, and then it's going to backtrack 2 meters to 3. Okay? And we're going to calculate the work done by friction. So the work is equal to the integral from 0 to 5 times what's the part of the friction force that's parallel to the path. So it's a horizontal path. What's the part of the friction force parallel to that? The component that's parallel to that. It's the x component, and if the object's moving to the right, which direction does the friction force act? To the left. So this is going to be a magnitude of 10 newtons, so negative 10, integrated over x from 0 to 5. And then we're going to have a second path from 5 to 3. What's the direction of the parallel part of the friction for this part of the path? To the whatever it is. Yeah, the path, right, the path is to the left, so the friction is to the right. Everyone following what I'm doing here? And so you get, what do you get? Negative 50 minus 20, so negative 70 joules. So now case 2, we're just going to go directly from 0 to 3. So the work is just the integral from 0 to 3 of what's the direction of that part of the friction, of the force? To the left, so negative 10 dx, and so we get negative 30. Okay, not the same. That's the idea. Yep.
I understand conceptually what you're doing, but 5 minus 3 is not 3, I believe.
5 minus 3.
Yeah, I was going up 5 and going back 3. And
This is the new one. This one's just going from the origin to the 3.
oh, it's the 3 location, now it's moving back 3. Oh, I was getting
Okay.
confused on how you do it. Okay. You did your math.
Thank you. Okay, so now let's do it with the conservative force. And I'm just going to make one up. Let's say we have a conservative force that's potential energy function is equal to 2x. Okay? So tell me the location in terms of x. We'll plug it in, and that'll give you the potential energy. That doesn't represent anything in particular. That's just an arbitrary potential energy function. Okay, so case 1. Let's do the two paths again. So it's going to go from the origin to 5, and then back to 3. So how are we going to calculate the work? Well, remember, the work for a conservative force is just equal to the negative change in potential energy. So we just have to calculate the potential energy at the starting point and the potential energy at the end point. So that's at the end point, it's going to be 2 times 3. At the beginning point, it's going to be 2 times 0. And so we get a total of 6 joules. For case 2, I mean, you can see exactly why it works this way. It has to be path independent because the only things that come into the calculation are the 2 endpoints. Okay? If you wanted, you could split it up into paths and calculate it based on the endpoints of the paths, but you'd get the same thing. So if it goes directly now, just 0 to 3, you can see from the way we do these calculations that won't have any effect on the result. It's still just the work is equal to the negative change in the potential energy, which is 2 times 3 minus 2 times 0, 6 joules. It has to be the same because the calculation only depends on the potential energy at the start and end locations. Okay. These are basically the only 2 potential energy functions, the only 2 conservative forces that we're going to deal with. So 2 potential energy, two conservative forces for this class. The first one is weight. And the potential energy for the weight is equal to m times g times the height. So notice that if your coordinate system is this one, the one we use most of the time with y up, then you can write this as mgy for calculations. And then the second one that we're going to do is springs. And for springs, one other thing I want to say about, this is an important thing to keep in mind when you're using the potential energy for the weight. So notice your choice of your h equals 0 location, what you're calling 0 height, is arbitrary. And the reason for that is, yep.
It's not. If you go over how you calculate delta U, the change in potential energy, because I don't understand why you got positive 6 instead of negative 6 like earlier.
Yeah. Oh, I did the, yeah, I threw away the negative. You're right. So this is the change in potential energy. You take the negative of that. So it is negative 6. Yep, thank you. I just calculated the change in potential energy. I didn't use the negative sign, so yeah, I got the sign flipped. Okay, so that makes sense, right? Yeah. All right, so this is an important thing to keep in mind about the potential energy for the weight. For any problem, your choice of where you're calling height equals 0 is totally arbitrary. And the reason that it's arbitrary is that when you're using, the only reason we're using potential energy is in the work energy principle. And so the work energy principle says all that matters is the change in potential energy. And so whether you call the height on the table 50 million miles or 1 meter or 0, all that matters is how much higher it gets or lower it gets. And so that constant subtracts out when you take the change. So all that matters in the work energy principle is the change in height during the problem. So we'll see when we start doing examples that you can make problems simpler by choosing your height equals 0 location in a good spot. Okay, the second type of conservative force that we're going to deal with is spring forces. And for springs, the potential energy is equal to 1/2 K times the change in the length of the spring squared. And we're always, for this, going to choose a coordinate system. Where the origin is at the spring's resting length. And the path of the spring, path of the object, is along an axis. So if you choose the origin to be where the spring's at its resting length, and say the object is moving along the x-axis, then delta L can just be replaced in that problem by x, and it makes calculations easy. Okay, we'll see how to do that. So now there's an important relationship between potential energy and the force applied by that conservative force. So there's an important relationship between a conservative force and its potential energy. Let's call this a potential energy function. The x component of the force is equal to negative du dx. And the y component of the force is equal to negative du dy. And so if you're given a potential energy function, you can figure out the force that it's applying based on this relationship. One thing that this requires, and this is an important fact about potential energy, is the force of a conservative force field always acts toward decreasing potential energy. Okay, so let's think about that in terms of gravity. So with weight, where is the potential energy due to gravity higher? Is it higher in the air or lower towards the ground? So U increases as the height. What? Here's the function. Increases, yep. And so that means that potential energy decreases as height decreases. And so which direction would you expect the weight force based on this to point? Down. And then that's, that's what we know it does. Phew. Imagine how confusing it would have been if we would have figured out that gravity acts up. Okay, so let's do an example of this calculation to figure out the forces. We're going to do two examples for the two conservative forces we're going to deal with all the time. Using this relationship and use it to figure out the force of gravity based on these potential energy, this potential energy function for gravity. And then we're going to do the same thing with the potential energy for a spring and figure out the force applied by the spring. And we know what those are, so we can use this as a way to sort of check the math. So the gravitational potential energy is mgh. So we're going to calculate the force vector due to gravity. Fx is negative derivative of u gravitational dx. So what do you get if you, and let's choose a coordinate system like this. And I'll choose h equals 0 to be at the origin, just to make this simple. And so with this choice, we can rewrite our gravitational potential energy as mgy. Okay, so what's negative du dx if this is the gravitational potential energy? 0. The y component of the force is negative du dy, and what's that? Negative mg. And so just what it should be. Okay, let's do the same one for the spring potential energy. So the potential energy for a spring, for the force applied by a spring, is 1/2 times k times the change in L squared. So let's set it up like this. Imagine a spring connected to this mass. And we'll use a coordinate system with x horizontal, y vertical. And we'll put the origin at the spring's resting length. Or let me be a little more careful about this. So we'll put the origin at the object's location when the spring is at its resting length. So then in this case, the potential energy for the force applied by that spring is just 1/2 k x squared. You see that? And so now we can calculate the forces. The x component of the force is negative derivative of the spring potential energy dx. So what do you get for that? Yep, and then negative, so negative kx. For the y component, what do you get? Derivative of u spring dy. There's no y in there, yeah. So, okay, so does this make sense? Think about the directions of these. So think about when x is positive, what's happening to that spring? When x is positive, that spring is being stretched, and so what direction is it applying a force? You know, the force that it's applying to this object, what direction is it, positive or negative x? Negative, because it's pulling on it. When x is negative, the spring's being compressed, and so the spring has to be pushing on the object, and so what's the direction of that force then? Positive. So that makes sense. Okay. Okay, so all this is coming to this final result. So using potential energy for conservative forces, we can rewrite the work energy principle and all we're doing is just breaking up the work into the part done by non-conservative forces and the part done by conservative forces. And you can go through this and see how the signs check out. But the new form of the work energy principle says that all the work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. It makes sense because the change in potential energy is equal to the negative work done by conservative forces. And then you can just add that to the other side and we get our original work energy principle back. But this form lets us take advantage of the simplicity that comes with conservative forces, treating the work as a change in potential energy. Okay. So now, after all that, we can start thinking about problems. Anybody have any questions about any of these concepts?
Can you go up to the formula again?
Yes. Mm-hmm. All right. So here's sort of a classic example of how to use this. One thing I want to point out is what happens if you don't have any work done by non-conservative forces? If there's no work by non-conservative forces, you can rearrange these terms again. And it says that the potential energy at instant 1 plus the kinetic energy at instant 1 is equal to the potential energy at instant 2 plus the kinetic energy at instant 2. And this is the equation that is often called conservation of mechanical energy. It's just another form of the work energy principle, just when this term W non-conservative is equal to 0. We're going to use this term, this form. Okay. All right, so let's say that we have a skier at the top of the hill. Hirsch. This is Hirsch. He's wondering if this is such a good idea. And let's say that this height is 50 meters. So first, let's say that there's no friction. And at the top of the hill, the skier's at rest. So if there's no friction, what's the skier's speed at the bottom? Okay, well, first we have to figure out what all the forces are acting, and then we're going to break those forces up into the conservative ones and the non-conservative ones. So here's an outline of Hirsch. Nice skis. He made them himself. That's what all serious skiers do. They carve them out of trees in their yard that were struck by lightning. Okay, so what forces are acting? Yes. No friction. Yeah. Otherwise, yes. But there's one more. The normal force, yeah. Okay, so the non-conservative forces that's only the normal force. The conservative forces is just the weight. But we have some good news here, since this is the part that's always potentially tricky, calculating the work done by the non-conservative forces. This part's always easy, calculating the change in potential energy. So we want, ideally, to have there be no work done by non-conservative forces. Are we lucky enough to have that in this case? Well, there is a non-conservative force, but if you remember last time, there were two types of, so even though this force is non-zero, it does no work because it's always perpendicular to the instantaneous velocity. So do you remember that last time I mentioned that any kind of force that's perpendicular to the instantaneous velocity does zero work? And the examples I gave were normal force and centripetal forces in circular motion. So even though this is non-zero, it doesn't do any work. So we're happy. All right, so let's write this out. So the work energy principle and let's choose a So the potential energy due to gravity is equal to mgh. Let's choose a coordinate system with y up. And let's choose, okay, so y is up. H equals 0. We can choose that wherever we want. Let's put it on the ground at the bottom of the hill. You'd get the same answer if you chose your H equals 0 to be the top of the hill or the top of Mount Everest or whatever. Okay, so what this gives us is that the potential energy due to gravity is equal to mgy. So now the work energy principle says we're going to be dealing with two instants. The one is at the top of the hill. That's instant 1. And instant 2 is at the bottom of the hill. So there's no work done by non-conservative forces. And that's equal to the change in kinetic energy. Do we know the speed at the bottom of the hill? That's what we're trying to find. So I'm just going to write this as 1/2 times the mass times the speed squared. Do we know the kinetic energy at the top of the hill? Zero, yeah. And now we'll do the change in potential energy. At instant 2, the potential energy is mg times y. What's y at instant 2? 0. That's what we chose as our y equals, as our origin location. At instant 1, what's the y value? Positive 50. And so this equation tells us that 1/2 mv squared is equal to 50 mg. Cancel the m's, multiply both sides by 2, and we get that v is equal to square root of 100g, or 10 times the square root of g. So that's equal to a little over 30 meters per second, 65 miles an hour. Which is why I guess you don't just go straight down. You do this thing. Because every time you do that, that's friction. Right? Hirsch could demonstrate better than me. Okay, so next time I'll start by doing the same problem, but just putting a little bit of friction in there, and we'll see how that affects the answers to this problem. Have a good weekend.